So we're going to talk about basic circuits, terminology. Now, I want to preface this by saying, I understand all of you have had engineering 120, 121, and 122. And so some of the material that we're going to cover, especially in these first few classes, may be familiar, but I am going to teach it, I believe, in a way that presupposes that you remember nothing from when you took 120. Partly because some of you do remember nothing. Some of you took it effectively all online last year during the full swing of the COVID pandemic and learned nothing. And so, yeah, probably just best to start with a kind of fresh slate. So before we begin developing techniques to analyze circuits, we need to make sure that we're all kind of on the same page with regards to the technical jargon that I'm going to be using. So the first thing that I'm going to introduce to you guys is just a generic circuit element. So this will be a generic circuit element, okay? This is an example of a two-terminal circuit element, okay? So we have a terminal up here at the top and a terminal down here at the bottom. And these terminals are how we connect elements together, okay? A two-terminal circuit element can represent a variety of electrical components. So it could be a resistor, it could be a battery, a capacitor, a diode. What it can't be are transistors and potentiometers and things like that that have more than 3 terminals. The overwhelming majority of the circuit elements that we're going to be dealing with in this class are two-terminal elements, okay? We are absolutely going to introduce a couple of 3-terminal elements, but most of the time, this is going to be, generally speaking, an appropriate model. So I can take these terminals and I can string elements together. So for example, let's call this guy here element A. And I'm going to put another element over here. And I'm going to call him element B. When 2 or more circuit elements are connected together, they form a network. All right. So where these circuit elements are connected together, or where their terminals overlap, if you will, that's what I'm going to call a node. Highlighted that guy in orange. So I'm going to give you a definition for a node real quick, and then we're going to talk a little bit about nodes. So nodes are points of interconnection between circuit elements. Now, a node, this fundamental definition of a point of intersection is absolutely correct, okay? But we can slightly expand it by understanding something, okay? When we talk about Ohm's law and resistance on Monday, I will explain why the assumption that wires have no resistance, which you guys all made when you took engineering 120, 121, and 122, is correct, okay? So the application of that assumption means that all of these wires that are connected makes this really one large node where elements A and B are connected. So we can lump those wires into the node. That's what I'm trying to get at here. And that's really going to make it easy for us to identify how elements are connected. Okay. So I'm sorry, was there a question? Okay. So if we connect even more circuit elements together, so let's make my pen weight not as heavy. Let's call this guy element C. This guy here, element D. When we add more circuit elements, we're adding more nodes. So let's do this guy in green. And this guy in light blue. Let me fix all the junk I accidentally erased. Yeah. So when we have multiple nodes present, I like to identify them using different colors because it helps me see and understand how the different elements are connected together, okay? So for instance, if we look at that orange node in the top left, we can see that there's really just a single point of interconnection between elements A and B, okay? Or there's a single node shared between those two elements, and that node isn't shared with anything else. Whenever that happens, those two elements are connected together in series, right? So a series connection is a connection between two, I'm going to underline this, circuit elements with no additional branching paths. So what I mean by no additional branching paths is that if we look at that green node, element B and element C are connected together, but there's a branching path out to element D, which means B and C can't be in series. Similarly, B and D can't be in series, and C and D can't be in series because there's another path that could be taken, all right? So only in this example here, only elements A and B satisfy the criterion for being considered a series connection. All right. Now, if we look at elements C and D, we can see that they share the green node at their top terminals, and they share the blue node at their bottom terminals. These two elements are considered to be connected in parallel. So parallel occurs anytime both sets of terminals are shared. Two or more circuit elements where both sets of terminal pairs are shared. Okay. So to refresh your memory of this, okay? C and D are in parallel because they share the green node at the top and they share the blue node at the bottom. Element B is not in parallel with elements C and D because while they do share the green node, B isn't connected to the blue node, just like C and D isn't connected to the orange node. So they can't be in parallel unless both of their nodes, the top node and the bottom node, are all matched to the same color, okay? So if we look at elements B and C, or B and D, these elements connection is not a series connection, and it is not a parallel connection. And that is perfectly okay, all right? That's one of the things that, from my experience of teaching engineering 120 series, is that a lot of students think that all of the elements need to be connected in series or parallel, and that's simply not true. They can be connected in a way that is neither series nor parallel, and there's nothing remotely wrong with that, okay? What we're going to spend a lot of time in this class doing is learning ways to simplify circuits to make them look like things are connected simply in series or simply in parallel, because that allows us to apply very simple circuit analysis tools. But in some cases, there are no simplifications to be made, and we'll have to develop stronger and more robust circuit analysis tools to handle those cases, okay? So not everything has to be in series or parallel. It is perfectly fine that some things are just connected, and that's it, okay? So I would like to take a moment and work an example problem with you guys. So let's say that we have the following network. I'm going to do it on a separate page because I think I'm going to come back to that one in a minute. I'm going to pre-apologize to the few students whose names I already know, because I'm going to pick on you all today. Eventually, I will learn most of your names and pick on all of you roughly equally, I think. So here we have a network that contains 8 circuit elements. So arguably a reasonable increase in difficulty from what we had previously, where we only had 4. So the first thing that I would like to do is to determine A, how many nodes does this network contain? Secondly, I want to know which of the elements, if any, are connected in series. And finally, I want to know which of the elements, if any, are connected in parallel. So let's see. Henry, let's start with you. We haven't talked in 2 years or whatever. How many nodes does this guy have? 5, okay. I agree, but let's go through the motions and identify them. So we have this guy in red, where A and B are connected. This guy in orange, the node where A and C are connected. This guy in green, which connects B, D, and E. This guy in blue, which connects C, D, F, G, and H. And then this guy in purple, which connects E, F, G. Henry, you were absolutely correct. There were 5 nodes in this network. All right. Let's see. I don't think. Apratana, am I pronouncing your name remotely correctly? Brittany. Okay, that's much easier for me. Thank you. Brittany, which of the elements are connected in series? So I like how you answered that question. A and B are connected in series, and A and C are connected in series. We will learn later, and by that I mean, I think Monday-ish, kind of another definition for a series connection that would tell us that C and A and B are all 3 connected together in series. But to understand why that is, we need to know a little bit more. So for now, I like splitting it up into 2 pairs of series connections. We will make subtle changes as we learn a bit more to expand these definitions. All right, thank you. Skylar, which of the elements are connected in parallel? So F, G, and H. So you split it up, F, G, and G and H, and there's nothing wrong with that. But a parallel connection doesn't have a restriction of only 2 elements. So we can actually lump them all together right now and be perfectly okay. Because F, G, and H all share the purple node on top, and they all share the blue node on bottom. So they all satisfy the criteria. So Anita, why isn't E in parallel with F, G, and H? Exactly right, because one leg of the element E is connected to green instead of blue, so it's not in parallel. That's as difficult as it needs to be. If they have the same colors on both sides, they're in parallel. If they share one color between exactly 2 elements with nothing else, they're in series. That's it. Okay. Doesn't need to be any harder than that. Anybody have any questions about this example problem? Hopefully, fairly straightforward. All right. So let's circle back around to this original network that contains 4 elements. All right. So when a network contains at least one closed path, the network can be considered a circuit. Okay. So this network is a circuit because it contains multiple closed paths. All right. So let's talk about what I mean by a closed path and introduce the concept of a loop. All right. So a closed path simply means, let's say that we started at the bottom left-hand corner of our circuit and tried to draw a loop around things, right? So we could start at the blue node, go through element A, go right through element B, go right, go down through element D, and we're back at the blue node. That's a loop. So if we start, effectively a loop is a path that starts and ends at the same node. How many different loops does this circuit contain? Close, but not quite. 3. Because any closed path is a loop. So let's write that down actually. So a loop will be considered any closed combination of circuit elements and nodes. So let me get 4 different colors here. Oh, I guess only 3. So the loop that I just talked about would be this guy, right? Effectively just going around the perimeter of the circuit. That is a closed path, so it is a loop. Now, what's your name, sir? Norman. When you answered the question and said 2, I would be willing to bet that you were considering this loop and this loop. Is that a fair guess into the inner workings of your mind, if you will? Okay. Those two loops that don't contain any smaller loops are what are called meshes. So a mesh is any loop in a circuit which does not contain a smaller loop. Our ability to correctly identify meshes is going to wind up being just as important as our ability to correctly identify nodes in our circuit analysis. Because in about a week and a half's time, we are going to spend a few days talking about nodal analysis and mesh analysis, which are extraordinarily powerful circuit analysis tools, where once you learned them, you are going to be so wildly frustrated at the crap that you had to do without them in your engineering 120 series that you're going to want to go fight whoever your professor was in the parking lot. They're that powerful, they're that useful. They are not wildly difficult to use, but they can provide us a ton of information about the behavior of a circuit. All right, so let's wrap things up by looking at this same circuit again, but now figuring out a couple of different things. How many meshes? Does this network contain? And lastly, how many loops? Does this network contain? So Maggie, how many meshes do we have here? 4. So let's identify them. I'm going to try to use colors that we can see that I haven't already used. So let's call this guy right here mesh 1. Let's call this triangular guy right here mesh 2. This triangular guy right here mesh 3. And this square guy right here mesh 4. Now to answer part E is going to be a little bit more difficult. So I want to break it down into digestible bits, okay? Maggie again, how many single mesh loops are there? Obviously 4, right? Because it's the 4 meshes we just identified. So I'm just going to call this mesh 1, 2, 3, and 4. Now we're going to have some 2 mesh loops. Running out of people whose names I know, so I might just start pointing to folks. Red shirt fella, I'm sorry, I don't remember your name. Carter. How many 2 mesh loops do we have? 3, exactly right. So there's going to be a loop that contains mesh 1 and 2. A loop that contains mesh 2 and 3. So we could effectively just draw a loop around that middle square by itself. And then we could have a loop that contains mesh 3 and 4. So it'd be like that triangle and that square on the right-hand side together. So I see a little bit of confused looks. So I'm going to draw something and then probably erase it shortly after because this is going to get far too busy if I don't. That's how we could combine mesh, or that's the path we could take for the loop that contains both mesh 3 and mesh 4. We could do something similar on the other side for the loop that contains mesh 1 and mesh 2. And then, like I said, we could just simply draw a square around D, E, and G and that bottom blue bit to describe the loop that contains meshes 2 and 3. All right. There should be some 3 mesh loops. How many? 2, right? One that contains meshes 1, 2, and 3. And another that contains meshes 2, 3, and 4. So effectively, this guy, and then we shift it over 1 mesh to get the other guy. And then finally, how many 4 mesh loops do we have? Obviously just the 1. So that would be the path around the perimeter of the circuit. Right? All right. So if all of this made mostly sense to you, we're all at least speaking the same language now, and we can start circuit analysis in earnest on Friday, where we're going to learn about the basic electrical quantities that we're going to be dealing with measuring throughout the entire class. So I hope you guys have a good rest of your afternoon, and I will see you all on Friday at 2:30.